Hello and welcome to this video showing how to solve recurrence relations using the characteristic root technique. I'd like to do an example where we solve the recurrence relation an equals 3 an minus 1 plus 10 an minus 2 subject to initial conditions a0 equals 4 and a1 equals 1. So let's get started. To use the characteristic root technique, the first step is to rewrite the recurrence relation having all the terms on the left-hand side equaling 0. So I'll just subtract the 3 an minus 1 plus 10 an minus 2 to the other side. That gives me an minus 3 an minus 1 minus 10 an minus 2 equals 0. Now from this, I can go to the characteristic polynomial and therefore the characteristic equation and then solve that characteristic equation to find the characteristic roots, and then we're off and running. So first, let's write down the characteristic polynomial. I notice I have three terms here, so I need a constant term, an x term, and an x squared term. My an will be the x squared term, so I write down x squared. My x term will be the negative 3, so negative 3x, and then my constant term will be minus 10. That's the characteristic polynomial. Setting equal to 0 gives me the characteristic equation. To find the characteristic roots, I just need to solve this equation. And in this case, it looks like I can find x by factoring. So let's try to do that. Let's see, an x there, they need to multiply to negative 10. So how about 2 and 5 and add to negative 3, so how about negative 5 and positive 2? Yep, that works. So that tells me the characteristic roots are x equals negative 2 and x equals 5. Now, I know something about the characteristic root technique, and that is that once I find these characteristic roots, I can go straight to my solution to the recurrence relation. The solution to the recurrence relation has to have the form an is equal to some constant, we'll call it a, times the first root to the n, so how about negative 2 to the n, plus another constant, call it b, times the second root to the n, in this case 5 to the n. Well, right there, that is the solution to the recurrence relation. Now, I can figure out what a and b are using my initial conditions. So let's go ahead and try that. I have these two initial conditions. When I plug in n equals 0, I should get 4. So I have 4 is equal to, let's see, a times negative 2 to the 0. Negative 2 to the 0 is 1. So this just becomes a. And then I have b times 5 to the 0. 5 to the 0 is 1, so just plus b. That looks good. Okay, and then I have, let's see what happens when I plug in 1. When n is 1, I get an output of 1. So a sub 1 is 1, and that's equal to a times negative 2 to the 1, that's negative 2a, plus it'll be 5b. All right, and now I have a system of linear equations, two equations, two unknowns, so I should be able to solve for a and b. And I've done it. So what I did here is I multiplied the top equation by 2 and added it to the bottom equation. That eliminated the a term and then gave me 9 is equal to 7b. Divide both sides by 7. I get b is 9/7, and since a plus b needs to add up to 4, I know a needs to be 19/7. All right, use whatever method you like to solve the system of linear equations. Once we have a and b, we can go back and get our final solution to the recurrence relation. I know an will be equal to, let's see, a is 19/7, so it's 19/7 times negative 2 to the n plus b is 9/7, 9/7 times 5 to the n. And there I have it. That is how you solve a recurrence relation using the characteristic root technique. Thanks for watching. Hope this has helped.